Alright, so what we're going to cover today is a fundamental sorting algorithm called merge sort. You're probably familiar with this if you've done any kind of algorithm class or computer science course. So what we're going to look at is why is merge sort n log n, what does the log even mean, and what are the fundamental routines or subroutines within the algorithm of merge sort. So before we were looking at n squared algorithms and quadratic time algorithms, now we are looking at the faster sorting algorithms, and we're going to see how merge sort pans out. So there are two subroutines that make up the merge sort algorithm. We will look at the code, we will look at the comparisons, and we're going to look at how this works fundamentally to the core level. So there are two subroutines. Okay, so we have the split routine and we have the merge subroutine. So what I want to look at first is the code for the split subroutine and what does logarithmic time actually mean. And first off, I want to say I have a video about merging two sorted lists. I have a video about logarithmic time complexities and really understanding what they mean. And like I've said, I had a video where I already covered this, but that was a while back, so I'm doing this again just so new viewers can see the actual content that I had before. Explained better, I think. So we're going to look at the split subroutine first. All right, so we have n equals 8, and we start with an 8, okay? So how merge sort works, if you're not familiar with it, is we split the input. We split until I reach a base case. Our base case is one item. One item is a sorted list. Our base case is when we have knowledge of what our input requires in terms of output. If I have a single item, that's a sorted list. If I have no items, that's a sorted list. Those are our base cases. So we have an 8 here. So what is merge sort going to do? Merge sort is going to do it depth first like this. It won't split it level by level. Let's trace it how the recursion will actually do it. So we have an 8. So we're going to split it one way. Okay, I split a 4. So we're going to split it again. Okay, we have a 2. And we're going to split it again. And remember, one item is a base case. I return to my caller. And then my caller splits right. And then one item is a base case. And now my caller right there has two sorted lists, and then the merge subroutine takes hold. And we'll get into the merge subroutine. We're just focusing on splitting right now. So we return back to the 2. The 2 does its merging in its level, and then it goes back to the 4. Okay, and now control is back here. And then it says I split right. So I split my input right, and then we split to the left. Another base case, and we return to the 2, and then we split to the right. Okay, and now we have this right here, and we had a base case, we return to the 2, now the 2, it does its merging routine, and then it returns to the 4. And now, 4 in its left hand has a sorted list. In its right hand, it has a sorted list. I merge the lists together. We're going to look at the merge routine time complexity, we'll see that, but now 4 has a sorted list. It returns back to 8. And now 8 has a sorted left portion. So now we're going to split and sort the right portion. And the exact same thing happens in a depth first manner. We go down and we're going to split. Do you see this level where we have all ones? We're going to split until we get all the way down here. So actually, let's trace the whole recursion just so you can see this. 4 splits down to a 2, and then 2 is going to go left again and split down to a 1. And then 2 will split to its right. Another base case, and now what we'll see is we're going to have the 2, it has a left sorted, right sorted. One item, that's a sorted list, one item, that's a sorted list, merge them, return a sorted list to my caller. And now, I want you to see that this has a left sorted portion, and now it'll go right and sort that. And then this guy says, how do I sort? I need to sort my left and right. Every one of these calls wants to sort their left and their right. They don't know how to do it, so they make more calls until base cases happen. Base cases know what they're doing. Base cases have an answer. We just return it upwards. So now we're going to split left. That's a base case that returns to the 2, and then we split right. Okay, and now 2 has a sorted list in its left and right hand. Merge them, return to my caller. Now 4 has a sorted list in its left and right. Merge them, return to my caller. And now 8 has a sorted list in its left and right. merge them, and return to the caller, and we see the caller was the original person. So what we have is, we have a sorted list. And why I use concrete numbers is, I want you to see the mathematical understandings behind why we have a certain amount of levels. So how many levels do you see here? How many times could I do a forking? How many split steps could happen? And we're analyzing the split function. So we have n equals 8. How many splits happened? 1 split could happen, 2 splits could happen, and 3 splits could happen. What does that say to us? This is why I made a video on logarithms in computer science. The understanding you need to have about a logarithm can help you a lot when analyzing something like this that's recursive and has cutting in half, which is what a log base 2 achieves. So what we see here is that we're going to have 3 levels of splitting, 3 levels of chopping things in half. But that's a problem. I don't want to be concrete anymore. I want to be literal with what I'm doing. I want to have this as a function of n. So how do I turn this, the amount of splittings, how do I turn that into a function of n? This is where logarithms take hold. We see that we're cutting in half every one of these steps. 8 becomes 4. 4 becomes 2, 2 becomes 1. So what we can re-express this 3 as is just log base 2 of 8, our input size, which is log of n. So do you see how this is slowly coming together? We have log of n. Remember that merge sort runs in n log n time. So this is going to play into that reason. We're slowly building our understandings until we can understand that original fact. So I'll re-express this as log of n split steps, splittings. And when I say log of n split steps, I don't mean the actual amount of split steps. I mean amount of levels that we can split downwards. So how many leaves do you see? How many base cases are there? What is the width of the bottom going to be? So we see 1, 2, 3, 4, 5, 6, 7, 8. So let me do that as a concrete number. So again, I see that there's going to be 8 things at the bottom. But remember, I don't want to have concrete numbers. I want things as a function of n. We could express the times we could split as log of n. But I also want to express how many base cases I'll have as a function of n. What do you see here? How do I get 8 from this original input of 8? Well, n is the amount of leaves we'll have. So we can just say n is the amount of leaves. Okay, so we're slowly piecing the facts together. We have a logarithm, log of n. What that asks us is 2. This is all a logarithm asks us. It says, to get the number n, what do I have to power my base by? Base 2. What does it need to be powered by to get the original n? We know that 2 to the what is 8, 2 to the 3, and that holds true. We can split 8 1 time, 2 times, 3 times until I get to a 1. That is where the logarithm is from. So how many leaves do I have? I have n leaves. As you can see down here, we have n leaves in this recursion call stuff. So what we now need to look at is, let's look at the actual code for the split subroutine so we can really hammer in and hone in on what this really looks like in code. All right, so here is some code / pseudocode for the split function. This is the driver. This is the key function that merge sort gets kicked off with, and it calls the merge function. So what I have in the description is a code sample. You can look at that, but I really want to talk over this so you really get an understanding of what is happening. I think that this code teaches the fundamental understanding of what recursion is all about and what passing off responsibility is all about, and converging to base cases. So our input is a list. This is with linked lists. You can do this with arrays. It doesn't matter. It's the same algorithm. So we have the head of a linked list. Don't worry if you're not comfortable with linked lists. It's the same process. So we have a base case. If I have 0 items, or if I have just 1 item, I return that item. I return an empty list, or I return the single item. That is our base case. Okay, there's our base cases, we converge to them. But what do we do in the recursive case? Well, all I need to do is, I need to find the middle. Since this is a linked list, we'll find the middle. We'll have a reference to the middle node. Call it mid, okay? So what we need is the split step. We need to sort the left half, we need to sort the right half. I call this function on itself. So do you see what's happening? Every stack frame has a responsibility. Its responsibility is to split left, split right. Split left, split right. We will keep splitting until this base case says, I know the answer, and then it pushes back upwards with a single item. Once we have a left half and right half sorted, remember, my left is sorted, my right is sorted. When I need to combine them is when I come down here. I say, caller, I will give you the left side and the right side sorted. How do I sort that? I do the merge subroutine. So this is the split subroutine. This is the splitting. This is the main driver of merge sort. And again, the code is in the description. I just wanted to talk this over because it's a great example of understanding how recursion works. This is the split subroutine. And now let's actually look at an exact or in detail execution flow that I did when I went to that forest thing one time. Yeah, roll it right now.
So we're going to walk through how merge sort would merge this input. When you see diagrams where they have those forks going down level by level all at once, merge sort does do the splitting of the input like this, but it doesn't do it all at once. It does it in sort of a backtracking way. So let's trace this and just follow along with me and you'll start to get the idea. So we start with the input and we split the input in half, we go left, and then we split the input in half again, we go left, and then we reach our base case of 19. This is where we return to our caller with the left sorted portion of the array 19.8, and then we go right, and then we sort the array subarray. 8 is a base case because a single element is a sorted array. Merge sort, the call to the merge sort function will always return a sorted array. So when we reach a single element, we do have a sorted array, so we can return that is a base case or an empty array. So we return 8, and then now we have two sorted arrays to work with, an array of 19, just 19, and an array of just 8. We merge those together into a sorted array and return it as the sorted array 8, 19. And now that is the left portion of the call 19.8, negative 13.2. And now we need to go right. So we need to sort negative 13.2, which is a subarray of the bigger array 19.8, negative 13.2. So now we go left, and then we reach our base case of negative 13, we return, and then we go right, and then we reach our base case of 2, and then we have two sorted subarrays to work with, negative 13 and 2. And now, once we sort them, we're going to have a sorted array of negative 13.2 to return as the right portion to our original call, 19.8, negative 13.2. And now we're going to have these two portions to sort. And then we have a merged portion, which is negative 13 to 8.19. And this is the left portion of the overarching call, which is 19.8, negative 13 to negative 5 for 130. This is the sorted of the left portion. And now at the very top of our call, we go to the right. And now we need to sort negative 5 for 130. And now we go left, and now we need to sort negative 5 and 4. And then we go left, and now we need to sort negative 5. Negative 5 is sorted, so we return, and then we need to go right. 4 is sorted, so we return, and then we have to merge two sorted arrays, one is negative 5 and one has 4, and then we return that as a sorted array as negative 5, 4. And then that is the left portion sorted, and now we need to go right. We need to sort 130, and then we go left, and then we need to sort 100. 100 is sorted, return. And then we go right, and then 30, and then 30 is sorted, return. And now we have two sorted arrays to work with. We have 100 and 30. We sort those, we merge those two sorted arrays, which we can do in m plus n time, or linear time with respect to each array. And then we have 30 and 100. And then next, we have the left portion and the right portion, which are sorted. And now we need to merge those into a sorted array. And then we get negative 5, 4, 30, and 100. And now we have the left sorted and the right sorted of the overarching call. So now we can sort them into our final result that we return as the answer. So negative 13, negative 5, 2, 4, 8, 19, 30, and 100.
Okay, so we need to analyze the merge subroutine. So I lost all the footage from the other video, so I'm just going to re-record this. I lost like 10 to 15 minutes of video where I explain the merge and the recurrence relation. We're going to do both of those right now. So imagine I have two lists. I need to merge them and produce a sorted list. So list 1 is sorted and list 2 is sorted. So the length of both lists combined is n. And what I'm going to do is I want to show you what is the worst case comparisons we will do, because later parts of the video will need this. So what we'll do is we'll put a pointer on the front of both of these lists. So what we're going to do is we're going to compare -1 and 1. Which wins? The lesser item wins. So -1 wins. So how many comparisons have we done so far? We've done one comparison and we moved this pointer forward and 1 got its placement. And remember, I forgot to say n is 6. Remember, the length of both of the lists summed together is 6. So what we do is 0 versus 1, 0 is the winner, place the 0, and advance. How many comparisons so far? We've done 2 comparisons, we put a placement, and we advanced. So now we do 1 versus 6. 1 is the winner. We've done 3 comparisons, and this is where our list stands. So now 2 versus 6. 2 is the winner. We have done 4 comparisons, and we're at this state right now. We're at this state. 4 comparisons so far. So we compare 3 and 6. 3 is the winner. Okay, we've done 5 comparisons now. And finally, we've ran over all of list 1, so we just place the 6. We don't do a comparison at the final end. And now what we finally see is, we see that we've done all of the sorting. Both lists are exhausted. How many comparisons have I done? 5 comparisons. What is n? 6. So what I can declare is this. What I can declare is that in the worst case, if I'm traversing through both of the lists exhaustively, the merge function, where n is the length of both of the lists combined, will do n-1 comparisons. So keep this in your pocket. We're going to need this for later when we're deducing the exact complexity, but it's n-1 comparisons in the worst case. So now let's look at the recurrence relation. So what is a recurrence relation? All a recurrence relation says is I want to recursively define what the answer to the subproblem is. So if I'm given an input of size n, what I'm going to do is I'm going to go left, I'm going to go right. And remember how the tree looks. Let me draw it very quickly. Do you see how we start with 8 and I cut it in half and over 2, I cut it in half and over 2. So what we're going to do is the answer for 8, or a generalized n, is going to be going left, going to the right, and then how much work do I do at this actual call? I'm going to do n-1 comparisons because this is split, 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 split. This is the work when I split left. This is the work when I split right. How much work do I do when I'm merging? n-1 comparisons. So what you see right here is the recursive definition of what merge sort is going to do. And what is our base case? T of 1 is 0. If I have one item, how many comparisons do I do? When I pass it into my merge function, this is what's going to happen. I'm going to have nothing, and then I'm going to have the one item. The one item will get the placement because there's nothing to compare against. So T of 1 is 0 comparisons. Again, T of 1 is 0 comparisons. So what I'm going to do is I'm going to solve this recursion going downwards. And we can merge these. These are the same terms, so they become this. All I'm saying is I have 2 branchings that each will split the work in half and will solve with that work passed in. So we have this, and then we have the work I actually do at the node. Split functions, merge. Split functions, merging. That's what's happening here. That's how I solve the work for a generalized n. So what I'm going to do is, why don't we solidify this and make this really clear, because I know that later in the video I'm going to prove this with a concrete analysis. So let's do it recursively, and later we'll see how we do it, solving for the actual exact amount. And you'll see what I mean. Check the table of contents as well so you can jump around this video because it's going to be long. Okay, so what did I just do? All I did was substitute 8. I plugged in 8 for n. There's nothing special happening here. So what does this now become? 8 minus 1 is 7, and 8 over 2 is 4. But there's a problem. I don't know what T of 4 is. But that's an easy fix. I already know the recursive definition. So what does this actually equal? See, all we did is, now n is 4. Well, technically the overarching n is not 4, but the input into the recurrence is going to be 4 right here. And all we do is simplify like we did before. So 4 over 2 is 2. And then 4 minus 1 is 3. Okay, we're solving for t of 4 now, so we can solve for t of 8. But to solve t of 4 so I can solve t of 8, I need to solve t of 2. So do you see how it's just building on each other? It's just recursion. So t of 2 is defined like this. Okay, so now we have t of 2 over 2. All we did is plug 2 for n. Before it was n over 2, now it's 2 over 2. And now we do plus n minus 1. 2 is n here. 2 minus 1. 2 minus 1 is 1. 2 over 2 is 1. And remember, our base case, t of 1 is 0. So this is just 0. And now we're going to start working our way back upwards. So we're going to do 2 times 0, which is 0, plus 1, which is 1. So the answer for t of 2, the amount of comparisons I do, if my input size is length 2, is 1. So what I'm going to do is, I'm going to evaluate this. 2 times 1 is 2. 2 plus 3 is 5. T of 4 is 5 comparisons in the worst case. So now plug that in. 2 times 5 is 10. 10 plus 7 is 17. And what we have is 17 comparisons in the worst case for when the number of input is 8. The size of input is 8. So we'll need this later when we're solving for the concrete mathematical formula for this. So why don't we go right back to it, and I'm going to send it back to Ben to analyze the tree. So let's go back and start seeing what the levels really mean now. All right, so we solved for the exact amount of comparisons, and what we're going to do later is we're going to solidify this into a solid function of n instead of a recursive relationship. So we just saw the solving of the recursive relationship, but we're going to see the solid solving of it later. So right now, let's look at an expression of the tree in terms of n. So let's return to our recursive tree. Okay, so now let's take ourselves to an investigation of the amount of work done at every single level. So at the first level, n is my input. How much work am I going to do at this level? Well, all I have is one subproblem. And remember, we know how much work we do at each subproblem, which is going to be n minus 1 comparisons. So one subproblem and n minus 1 comparisons. And I don't want you to be tricked by n. N means the size of the original input. This n here is this n there. So I want you to remember that as we branch this tree. So let's branch it again with 2 forks. Okay, we just branched, and how many subproblems do I have? I have 2 subproblems. So write that down. And again, we're trying to find the work in every level. So what we have here is 2 subproblems. How much work do I do? Let me write the minus 1. Okay, I wrote the minus 1, and now I want you to see what is the size of the input to each of the calls to merge. The size of the input as a expression of n is n over 2, n over 2. We split downwards. I can't put n there. I put n over 2. Remember, the key here is we need to always keep in mind what n really means. N is not the input size at each call. N is the overarching size of the original list. And these are fractional components, and therefore the work is going to be a fractional component there as well. So let me shift over to that side. Okay, so you now see this is what happens. And why don't we split it down another level and see what the amount of work in that level is? Okay, we split it another level. And what I'm going to do is, how many subproblems are in this level? Well, we're going to have 4 subproblems, and we can write the 4 right now. And as a fractional component of n is the original size of the input, not the size of the input at each of these levels. What we can do is, we're going to put n over 4. That is the size of the input as a component of the original input, because that's what just happened. We split, and what we have at this level is that exact quantity. So it becomes n over 4 minus 1. And what we're going to do is, we're going to keep going downwards. So let me express that. And now is the time where we notice our patterns. So I want you to remember that our input size is n. And I want to re-express everything as generically as possible. I don't want to hard code this 4 here. I don't want to hard concrete put these numbers, right? So let's re-express this in terms of n. So what is this 1 right here? Would you disagree if I did this right now? What is 2 to the 0? It's going to be 1. Would you disagree with me if I did this right now? 2 to the 1 is 2. 2 subproblems, level 1. Would you disagree if I did this right now? 2 squared is 4. And okay, I expressed that as a function of the level, and now we have 2 to the 0, 2 to the 1, 2 squared, and now I want to re-express these n's in terms of what level they're sitting at. So would you disagree if I did this? So you see that right now. All I did, I had an n before, but now it says n over 2 to the 0. n over 1 is actually 1. So would you disagree if I did this now? I re-expressed n over 2 as n over 2 to the 1. And I want you to start seeing a pattern here. So I'm going to re-express this right here. What is 2 to the something to get 4? 2 squared. So now we're really starting to see what the work is. So I would go as far to ask you, what is the generic way we can express work at each level? So let's let I be the level that I'm on. So how much work do I do at a level? So this is level 0. Notice I say 2 to the 0. So let's say 2 to the I, because the I is the level. And now what's inside? We have n over what? 2 to the level. Do you see how it says 2 to the 0, 2 to the 1, 2 to the 2, right? So let's say 2 to the I. So that equation we have right there is the generic equation for the amount of work at the ith level. So what I want to do is to find the worst case work. To convert that recurrence relation into a solid mathematical formula, I want to find the sum of the work across every single level. And now this is where we get exact with what we're saying. This is the formula we have in our pocket. Before, what do we have in our pocket? What is going to help us? N minus 1 comparisons for the merge routine at worst. And what do we now have? We have the ability to express the amount of work at every level. So if I want to know the work across all of my algorithm, all I need to do is take the sum. How much work did I do here? How much work did I do here? Here, here, here. And then we will have an exact upper bounding. And remember how we solved the recurrence with the 8? What we're going to do is we're going to solve the concrete equation we come up with from taking the summation over this guy. So why don't we build that summation right now? Okay, so now it is time to build a summation. We've done this before. We did it in bubble sort, we did it with insertion sort, we did it with selection sort. So now let's build a summation. So let me start our sum right here. And how many levels do we have? Well, we can start at the 0th level, I equals 0. And then what is the maximum amount of levels I'll have? Well, let's look at this. This is where the indexing shifts things, but I want you to watch this. So how many levels do I need to sum over? What's my upper bound? Lower bound is 0, okay? So if n is 8, imagine that. We split this many times. Log of 8 is 3. 3 splittings, right? So 3 splittings, and we have up to 2 levels in terms of indexing off 0. We're just switching our indexing here so that we can run a summation. So we go from 0 to 2. How do I express this in terms of logs? I say log of n minus 1 is 2. So this is what our upper bound becomes. There's nothing fancy happening here. All we're saying is the amount of levels minus 1, because now we're indexing off 0 instead of 1, is the upper bound. So I'm summing level 0, level 1, level 2. Level 0, level 1, level 3 minus 1, which is 2. So nothing changed there. Now I have my bounds, and what goes inside my summation? The amount of work at every level. What was that? If we remember back, it was this. Okay, so we're going to be doing a little math here, and don't get lost at any step, because I don't want this to be about the math as much about the deeper understandings, because you can always go and brush up on summations and doing these simplifications, but the deeper understandings are more important. So we're looking for the exact amount of comparisons across the whole algorithm. We're summing across every level, level 0 to the amount of levels minus 1. So that is what's happening here. And what I do is, let me distribute the 2i in. Okay, so my summation stayed the same. I didn't write these small terms, but just know they're still there. So now all I did, distribute the 2i in. And you see these guys cancel, and we're left with n minus 2 to the I. So let's express that. Okay, so that is our new equation, and what we can actually do is split these and subtract the summation. So watch what happens here closely, right? So does that make sense? All I did was split the summation into the summation over n and the summation over 2 to the I. So we have these steps so far. So what we can do is we can re-express this. And I'm going to write this as a solid formula. So all that happens is both of my summations now yield this. So I have this summation, this summation. The sum thing is the same. The sum sign is the same, but what our terms have become is split through our simplifications. So what we can do here, we can simplify this. We know how to do that. We can do top bound minus lower bound plus 1 times the inside term. So just watch this. Top bound minus lower bound plus 1, that plus 1 there so we don't forget about our bounds, so we include the bounds. And what we need to also do is multiply by in here. So this is how many times the summation runs, and we're going to be doing this every single time, adding n over and over. So multiply that by this expression, so n times this. So we can simplify this. So what is log n minus 1 minus 0 plus 1? Well, 1 minus 1 is 0, and 0 minus 0 is 0. So all we have left is log n. And this is one of the magical moments when you're actually looking at this, is all your life you were told that merge sort is n log n in the best, average, and worst case. But why is that the case? What's the real meaning behind it? Well, our highest order term in the worst case is n log n. That's it right here. This is the reason our big O upper bound is n log n. All of these other guys over here are going to be factors that get dominated by n log n. And this is why merge sort is n log n. It's right there. That's it. So let's finish off this guy so we can see the exact amount of comparisons in the worst case. So let's do some simplification there. And let me introduce a rule that is kind of confusing, and I don't really want to go through how it's actually deduced because it doesn't matter. But here, look at this rule. Okay, so I don't want to lose you here. So look at this. This is how we're going to solve this. This is just a concrete statement of what this summation actually says. So we say 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4, so on, until our last term, I is this as the last term, 2 to the log n minus 1. So what happens is our r here is going to be the base. It's going to be the base we have right here. So just stay with me, follow me. So r is our base of the exponent right there, or the base of this exponentiation. So what we're going to also do is we need to know the upper bound. When do we stop? What is the last term? And the last term is going to be log n minus 1. Okay, so what happens here is we're going to plug in k and r into this equation. And I'll have a link below for the derivation for this if you're really interested in it, but that would take up too much time here and get us off the main point of this, which is merge sort. But what this becomes is this. We're going to plug in and simplify. Okay, so we plugged in r and k here. So we plugged in r, we plugged in k, we plugged in r. And they match, these match. So let's simplify. 2 minus 1 is 1. Log n minus 1 plus 1 is just log n. And now we have this expression over 1, so it just becomes the expression itself. And I'm going to write the base of the logarithm just so you notice a little pattern here. And then I wrote some parentheses just so you don't get confused. This is the extraction of that. So we have a base of 2 right here, and then there's a base of 2 on the logarithm. So what happens? This is a logarithmic rule, and it looks like this. Again, I'll put a link in the description, and there's an intuitive understanding behind it. But what happens is this is just the same thing as what's inside there. So if I have the same thing right here, 2 to the logarithm with the same number here as its base, I just reap that number right there, and it becomes n. Again, I'll have links for these more complex steps in the description for your further investigation. And finally, we have n minus 1, distribute the negative sign in, and what do we find? So the amount of comparisons for merge sort in the worst case, the upper bound we can provide, is this exact amount. N log n minus n plus 1 comparisons. This is how much work we will do total given an n. So where does n log n come from? Why is there n log n? Well, it's right there. That's the big O boundary. That is where it comes from. There's no mystery. This is exactly why. And what we also need to think is, whenever we see a log n, always think of splitting. So that's where the splitting came from, log n splitting. So why don't we use this to solve what we solved before? We are not using the recurrence now. We're using a concrete mathematical statement. So let's plug in 8 as n and see what we find. Okay, so look at this. N equals 8. Remember how we solved the recurrence before? Now we're going to solve the exact statement and see what we get. Is it the same? Am I right or wrong? I'm not sure. So what we're going to do is 8 times log of 8 base 2 is going to be 3. So 8, negative 8 plus 1 is 7. We have 8 times 3 minus 7. That becomes 24 minus 7. What is 24 minus 7? Well, 24 minus 7 is the same thing as saying this. So what we have here is we have that this is 17. And if we think back in our memories, we saw this before. 17 comparisons. When n is 8, we got 17. So that was the concrete deduction summing the work across every level. And this is the same thing we got with the recurrence, going down to a base case. So this is how merge sort works. The code is in the description for you to investigate further. So that is all for this video. If you like this video, hit the like button and subscribe to this channel. My goal is to make this one of the world's largest software engineering resources for software engineers to prepare. Every day I work to make this a larger and more helpful platform for people to learn from. So that is what I work for, and I don't think I'm going to be finished until the technical interview system is the way that we want it to be. So yeah.